we have just started the quiz, so look at the answer. Try to answer them within 15 minutes.
Okay.
Okay. Yeah. Pretty sure. Okay, we got 2 more minutes to go. It is pretty straightforward, the quiz, right? If you get all the different models correct for the past couple lectures, it's pretty straightforward. So it's also given me a chance to see your understanding of it. Yeah, thank you. No worry. If you're down, you can pass to your classmate to the left. I'll collect on the other side of the table, okay? So you. All right, I got it. Thank you. Perfect. We got everybody's quiz answer? Is someone left? Okay, there's a couple more there. Let me pick them up, then start today. Thank you. One more? Okay, great. So, all right, welcome back, everybody. So, I hope everybody is still feel very good about the class after the first homework. Like, my philosophy is homework is hard. So I think some of you talk to me on the homework. I'm glad you do that. So if you still have questions for the homework, feel free to check with me. What we're going to do is I'm going to grade the homework this week. Then next Tuesday, we're going to discuss the question one by one on the board with everybody. Okay, make sure everybody understand that. The quiz is also a good way for me to understand everybody's understanding for those conceptual ideas related to the quantum physics model. So we're only going to do a few conceptual ideas down the road to make sure everybody is following the topic. And it's given me some feedbacks what we should emphasize again, okay? So today's lecture, we're excited to talk about the chain rigidity for polymer in general, okay? So why we need to do chain rigidity, we explained a little bit last lecture. Using 3 different models, you guys did the quiz. It tells you how we can understand the size scale, right? We only discussed end-to-end distance in the first couple lecture. We can see how big you are depends on bond length and degree of polymerization, or number of bonds to be more accurate. And in the homeworks, number 1, everybody should have a taste about what is the end-to-end distance looks like. And I want to engage a little bit more on the homework. So as you can see, when we measure the sample, we don't necessarily measure the length scale of number of bonds, right? But we do measure the indirectly in the next couple lectures. We're going to talk about radius of gyration. But generally speaking, from the homeworks, you can understand, depending on how your molecular weight depends on the length scale, you can understand how rigid your polymers are, etc. So those are all intertwined. So today's lecture, we're going to go a little bit deeper, how we understand the persistence lengths, how we calculate them, and what is the consideration people had when they developed this persistence length concept. Okay? So we chatted about in the last lecture about different length scale in the coil, in the garden hose. Persistent length is a good way you compare with your polymer chain to understand. So a very interesting homework we did a couple years back is a stainless steel rod, like in the construction site, is it rigid or it's flexible? How many of you think it's flexible? Oh, I love this class because you always give me different perspective. The answer is really, you need to understand what size scale we're talking about. A classic example also relevant to the polymer is when we talk about persistence length, you need to understand the persistence length with respect to your length scale of your polymer if you talk about its flexibility. So in other words, I want to emphasize again the stainless rod. Thank you for offering a different perspective, flexible, right? If it's long enough, then it is behave like flexible. Depends on length scale. If within a feet, yeah, it's rigid. There's no way we can bend it. It's just the property we take advantage of that. But you also probably heard about those skyscrapers, 100 feet, 200 feet, 2,000 feet building could swing in the wind. So they're flexible to some degree. Same for polymer physics. When we talk about flexibility, we need to understand a relativity with the length scale of the molecule. So what's the length of overall? So that comes down to, we should compare the contour length, LC, the total length of your molecule with respect to this LP value. So if your LC, the total length of your polymer is much bigger than LP, the persistence length, then it's basically behave like this. We call it flexible, okay? And if your LC, which is contour length, and LP is persistent length is on the same order, or even in some cases you might calculate the LP is bigger than LC, theoretically you should consider your polymer is like rigid rod. Piece of stainless steel, but at much length. So it's relevant. It's like philosophy. It's relevant, depending on what scale you're talking about. But for most of polymer, since LC contour length is relatively in a relatively small range, if you given the molecular weight of most polymer we deal with in the lab or in the commodity is somewhere between few 10 kilodalton or few 10 kilograms per mole to a couple million. So typical length scale for LC is on the order of tens of nanometer to up to a few hundreds at most. Okay? Very common. So now I want to give everybody a few examples what the LP value looks like for several polymer. So if you think about the textbook we talked about in Lodge's textbook, there is a table actually listed a lot of persistence lengths for many commodity polymer. Let's start with some of the common ones, like polystyrene is some of the common one. It's typically on the order of 7 to 8 angstrom. So if you compare 8 angstroms versus 20, 30 nanometers, so your LC will be much bigger than LP. So your polymer is behaved like flexible core. Okay? And that's typically the case for many commodity material, polyethylene, polypropylene. They don't have any structures to limit your polymer to go in one direction. In the field I work with, we deal with a semiconducting polymer. One of the characteristics of that is you have alternating single and double bond along the polymer backbone. So double bond will make your backbone more rigid, or some of the case like PET, if you have a lot of fused ring, then your rigidity will go up. But we're still talking about LP on the order of just a few nanometer to tens of nanometer, okay? So example would be polysulfing is some of the polymer I deal with. It has a 5-member ring along the backbone, and you have LP about 3 nanometer. So 3 times or 4 times bigger than polystyrene, but not too high. So we call it semi-rigid, and we will cover it later. Or in the textbook, we actually call it worn-like chain. So something like this, semi-flexible. So what is like a really rigid? Some of the newer development that my colleague, one of them in Tamil University is developing is called ladder type polymer. So not only you have a double bond, you have all fused the ring around the backbone, then you could have very rigid structure. He haven't measured the persistence length, but we expect to be tens of nanometer. The other one that everybody familiar with is double strand DNA. So everybody has a DNA in a body. So they are regarded as rigid, and those structure has a persistence length typically on the order of close to 100 nanometer, okay? Or even some of them higher. So DNA, if it's low molecular weight or shorter, it is a rigid rod. But if you make very, very long DNA, it's like you have a kilometer long stainless rods, it will still have a lot of flexibility, okay? So when you discuss about flexibility, always understand it under the context what LC and LP is. So with that sorted away, so actually how do we describe this LP in a mathematical way that we can evaluate depending on our chain model? So that's our job today, is to go from conceptually, everybody I think has a reasonable understanding about persistence length, to be more advanced in the mathematical way how we gauge these persistence lengths, okay? There's a couple concepts I want to sort it out away, which we should have done a little bit early. So chain statistics. So there is interesting things regarding how people take advantage of different chain model between free joint chain and rotation isomer chain, etc., etc. So one thing that in the homework we asked the equivalent statistical segment length or the value of B. So let's define what this B is. Everybody understand, sure by now, what is a characteristic ratio and what does free rotation chain and hindered rotation chain has a certain impact for this characteristic ratio. If you are free joint chain, then you just have NL squared. There's no resistance expansion factor. But a lot of time, when we do physical models, it's just much simpler if you don't have that prefactor. So some of the physicists come up with a very smart idea. They say, this could be a polymer chain, right? From one end to end. It's a little bit extended conformation, but that's not the point we want to show. So if you look at the end-to-end distance, we have another way to have a second set of the bond that shows in red. If we join them, they would ended up at the same length scale, the contour length. So black chain and red chain, two different colors, had the same length. But if we can replace the black chain, which is defined by hindered rotation chain model, replace with a free joint chain model. And replace with the free joint chain model has two new set of parameters. One is N, dP, basically degree of polymerization. Then we can bring up a new parameter called B. B is called statistical segment length. So the physical meaning is, if we don't worry about the real length of, let's say, PET, etc. in the homeworks, if we assume we know what the N is, if we can use a free joint chain to describe our chain in a similar valid way, then we're in good shape. Why? Because the model is much simpler. We only need mb squared compared to NL, C infinity NL squared. We basically replaced a hinder rotation or free rotation to free joint chain. And the more you learn, you will see free joint chain is preferred in many cases. It's the simplest, and without worrying about the bond angle, simplify many things. So in this case, the statistical segment length is basically, we want to replace a hinder rotation chain with a free joint chain that they will have the same LC contour length and the end-to-end distance. So that's where this B value comes in, okay? So in other words, if you think about PET in the homeworks, if we don't look at the bond details, we can just replace them with this big red bond and have a certain length. It will be able to describe your PET as good as you consider all the bond angle. And we talked about the characteristic ratio. Characteristic ratio, I think a lot of time unofficially I explain the physical meaning. It can be related to expansion ratio. And I also alluded to the point this value is tied into the rigidity of the polymer chain, right? The more bond angle, more defined, you're going to have a more rigid structure. So in this case, there's, again, two ways you can define that. You can define it to be effectively with M bond, with effectively bond length, LE effective. That's one way you can describe it. Compared to the other model we call equivalent statistical length, now you just fix the N and trying to find the effective L to describe it. In the previous case, we defined N, then find a statistical length to define. Either way, they serve both the purpose of replacing a hinder rotation chain to a free joint chain. Okay, no difference. So if we look at here, we know LK is cone length. Cone length, actually, using the equivalent model, we can link the cone length with the characteristic ratio, which is given by this equation. So LK would be equal to characteristic ratio. For example, for polystyrene, that's value of 6, 7, around there. L is the monomer bond length, and divide by sine theta, divide by 2. Okay? So in many cases, persistence length will also be treated in a similar way. But we have a way to further simplify this, depends on this bond angle. Okay? So this particular slides, we show statistical length is what we have shown in previous slides. It's a conversion of hinder rotation chain or rotation isomer chain. So that's where C infinity is. Number of bonds, bond length, will be equivalent to degree of polymerization and statistical segment length. Okay? The statistical segment length then would give you many unique ways to measure your structure. So one of them will allow you to directly probe R squared divided by N equals to a value, and that's what we did in the homework one. And we're going to come back to explain details for the homeworks, how we actually use this to back calculate C infinity. I'm looking forward to grade the homework and see how everybody do here. Now come back to the persistence length. We talked about the persistence length is basically the physical meaning of persistence length is how rigid your polymer chain. And the other way people describe it is the ability for your chain to maintain its directionality. So here is a picture of the garden hose. So along that at different length scale, it's behaved very differently. At the very, very small scale, let's say within this length, it's behaved like pretty rigid rod. And on the larger scale, it will become flexible. So we just need to measure this LP values, then understand what the length scale you are compared with LP. If your length scale is smaller than LP, it's behave like rigid rod. If your length scale is trying to compare as much bigger, then it's flexible. So turns out there is a pretty nice way to describe persistence length. So let me explain this equation. This LP is persistence length. Is this not equal sign? That's the definition. So it basically means LP is defined as 1 divided by L. What does this mean? This is basically a normalization. Okay? So I'll write on the board just a second to explain what this part. And we know the dot product, what that means. L1 dot R. So LP basically defined as what is the projection of your R along this first bond direction. Okay, so if we review a dot product, so this is theta. Let's write it as use L1. This is L2. Okay. So the dot product L1 dot L2 will be equals to L1. Convert this vector to scalar L2, then cosine theta. So we basically has a dot product which is final value. Why we need to normalize by L? If we divide by L, which is defined as, again, same as vector, then as scalar, then this L1 length will be removed. What left is L2 multiplied by cosine theta. If you look at this interesting triangle relationship, let me write L2 again, bigger. So that's where the direction of L1 is going. So if we do L1 dot L2, we would also consider what the length of L1, but we don't need that. We only need to see what is L2's directionality along the L1. So that's why we need to normalize this particular term L1. It needs to take average because we want to average out every single bond. What this R is end-to-end distance. So this can be translated to exactly this. L1 all the way add to Ln. So persistence length basically defines as we need to examine every single bond's projection along one bond's direction. So L1, how much it's projected to L1's direction. L2, how much it's projected to L1's direction. L3, how much component has left in L1 direction, and so on and so forth. Okay? So basically, this is a general definition of the directionality of your polymer chain along a given bond direction. And it actually doesn't matter if it's L1 or not, because this is universal. If you replace L2, this is the same equation. So for free joint chain, then what is LPS? For free joint chain. Free joint chain. Simplest case. L, right? So free joint chain basically says there is no limitation of where the bond angle are. So your persistence length or your chain's directionality will be lost just after one bond. The second bond, they basically say, I don't care what my predecessor thinks. I can go anywhere I want. I'm not influenced by my predecessor. So if you look at this equation, it's basically L1 dot L1 is going to be L squared. average of L1 dot L2 for free joint chain, the average, this will be 0. This will be 0 again. So it's also reflected in this equation for free joint chain. LP will be equals to L squared divided by L. That's basically one bond length. This I already alluded a little bit. That's a definition of persistence length. And this is looking at projection of L2 along L1 direction. Okay, the directionality. If L2 is following the majority of that direction, that means the angle of L2 will be defined fairly close. And this red line defined as L2 absolute multiplied by cosine theta. Theta angle is this one. If the angle is bigger, if you look at what is L3 multiply the projection on L1. So this is bond 3, right? 1, 2, 3. So we need to consider this bond projection in L1. And you can see it follows a less portion of directionality. So we have a decay the longer the length it goes. Okay? So, which is shown by here. So for any bonds, if we generalize to count any angle's directionality, then we can generalize using this particular equation. The longer the length, the more loss you have, right? So for any bonds within your polymer, if you count your bond is Li, bond I and J, you can simply understand this is the projection between the bond and J. You just need to count the distance between these two carbons. I minus J absolute cosine theta power of that. So if they're neighboring chain, if I'm looking at bond 5 versus 3, of neighboring there must be 5 and 4, then you can use 5 minus 4. So you know next bond projection to the previous bond will follow exactly 1, 2, which is 1 cosine theta. If you want to look at the third bond projection with 1, you need to consider twice this theta angle because L3 need to project to L2, which is 1 theta angle projection, and you need to project it one more time. So that's equals to cosine 3 minus 1, which is cosine square. So now if I consider what is the bond 1 and its correlation with bond 100, it can be also described by this equation, right? But that will be very little. Why? Because L squared is a constant. Cosine theta power of I minus J, I in this case will be equals to 1. J will be 100. So you need to have a cosine theta power of 99. And we know the cosine theta is less than 1. The more times it multiplies by itself, the smaller it is. So in other words, bond 100 is not going to remember anything what it once said. There was in the when I was little, there are some of the TV shows was interesting, was talking about somebody tells A a phrase, and A need to tell B, B need to tell C, so on and so forth. Then people are tracking how they actually translate, and by drawing it on someone's, by drawing it out, and somebody recognizes what the first message is. It's the same. The longer you relay the message, the more it's getting fuzz and dilute. Same for there. Okay. The longer the bond with distance is there with it, the less it's memorized its original directionality. So that's where then persistent length will always have a finite number. Right? Remember, if a polymer coil, I walk around the backbone, after a couple of chain, I probably don't remember the first chain because of this reason. So for the flexible chain that we know, we can define using the above simple equations 2NL r squared. R squared is again end-to-end distance. And in this case, end-to-end distance is already described, right? And 2NL is described by previous equation if we calculate adding everything together. So this tells you the conclusion how characteristic ratio depends on persistence length. In a simple words, they scale proportionally because L is constant. So you don't change L. You change polymer, you change characteristic ratio. Bond, carbon-carbon bond, if it's the same backbone, then it doesn't change, right? So LP scale linearly with the characteristic ratio. So it's kind of make great sense when we teaches everybody at the beginning. The more rigid the polymer are, the end-to-end distance will be bigger, end-to-end distance is bigger. Or in other words, if in the expansion ratio when we talked about free rotation chain, when the bond angle is bigger, when the chain is more tend to be more pointed in one direction, when the theta angle is close to 180, then you have a much higher characteristic ratio and persistence length. Okay, this is how everything could be tied together. So if we look at the cone lengths, what we have discussed at the previous case, these two are quite similar. If we have to put a value, if we sin theta, it goes to larger bond angle, it's closer to 1. So in that case, if this equals to 1, cone length will be equals to roughly twice of persistence length. It's basically two ways people describe them. So one is called cone length, the other is persistence length, okay? And more commonly, I would call persistence length is more commonly used, although they a lot of time used interchangeably. They can both describe how rigid your polymer chains are. Okay? So 2 parameter, same ability to describe how rigid your polymer are. And we also discussed briefly how characteristic ratio are linked to the persistence length. Okay, so I will introduce this part, then we can come back to this part given the time we have today. So in the next class, Chantal, please.
I have a question about the last slide.
Yes.
Is theta always going to be 180 for flexible chain?
No, no, that's not the case.
Okay.
So this particular case is trying to show you what is potential LK and LP depend on what the extreme case in the bond angle. Okay. So we talked about flexible chain. We talked about all these different models. If everybody recall, there is one kind of general assumption is you're made of a relatively flexible backbone. If you go back to read the Tim Lodge's textbook, a lot of first part is talking about, again, mirroring what we're talking about, persistence, length, infinity, and L square. In this case, you need to worry about 2. And whenever there's an exponential term, I know people are like, oh, how do we plot the results? So we're going to come back to the next class. But generally speaking, this is a polymer chain, can describe both rod-like chain and coil chain. And it covers this transition zone in between. I'll talk more in next class what is this transition zone means and how one-like coil actually would be able to fill the gap between a flexible polymer and a totally rigid coil. Okay, in 2 extreme. One last thing to check one. So, flexible chain, we have already a model, right? Because all 3 quizzes, all the quizzes are related to this flexible polymer chain. We also have rigid chain. Rigid chain is easy. The extreme case is a rigid rod. Not much you can describe, right? You just need to know the bond length and number of bonds. So the contour length will be n multiplied by L. Probably simplest. So this is where the next lecture will cover what if you are somewhere in between the one-like chain, how do we cover that? Okay, so we're going to finish today's lecture. Any question for today's lecture, please?
So in a rigid chain, the persistence length is greater than the contour length? And
Yes. It's on the similar order. I would rather put it that way. And of course, it depends on how you measure them. Sometimes when you measure, it could be, as long as they're on similar order, we call they are very rigid.
And if so the persistence length is, conceptually defined as the length that the chain will go before it goes 90 degrees.
Yeah, I think cumulatively when the chain would roughly bend 90 degrees, because it's never be a sharp bend, unless it's free joint chain, right? Then go one bond, then it's bend 90 degrees. If you think of free rotation chain with a bond of 109 degree, because one bond is going to be bent slightly, and then the next bond will be able to reach that. So if we look at the persistence length with a bond angle of 109 degree, if you calculate that, that will be equals to characteristic ratio roughly about, I think they're roughly about 2, what we have calculated, right? So your persistence length will be equal to roughly characteristic ratio divided by Q multiplied by L. But there is one caveat. When the C infinity is small, then it starts to lose its ability to capture because C infinity 2 divided by 2 equals to just 1 LP. It doesn't make full sense. But if you think about polystyrene, in that case, the characteristic ratio is roughly about 7. So you use 7 divided by 2 and multiply by L. That's roughly LP. That means after 3 or 4 repeating units, it's already has ability to lose its directionality. So for most of flexible chain, that is a very tiny distance. Typically less than 10 carbon-carbon bond. It will lose directionality or has the ability to swing by 90 degrees. Okay. So extreme cases are if your backbone are made of chains 180 degrees, then you can see it's always going to maintain its persistence length. Or you have a lot of fused ring like benzene ring, sulfine ring, 5-6 member ring, etc. That will make your polymer special. However, if you look at the table on Technologist textbook, most of commodity polymer like PE, PP, PET, PS, PVC, all has persistence length less than 1 nanometer. What that means, 1 nanometer divided by bond length of 1.5, that means the directionality is lost quickly. The polymer are all flexible for those commodity polymer. Unless you play with some specialty polymer, example could be those liquid crystalline material or Kevlar fibers. These Kevlar polymer are made of aromatic rings. Those are much, much more rigid. So these gives rise to some unique properties such as ability to form liquid crystalline phase, ability to have a high TG without, if they are not have much side chain, then they are linked. Okay. Any more questions, please?
Question.
Yes, please.
Isn't B the statistical segment length representing one repeating unit?
So the physical meaning, let me repeat that one more time. Very good question. I like it. So what is statistical segment length? So statistical segment length B, if you think about in the real polymer chain, you have a certain bond. And typically you have oxygen, all kind of different things. In the PET, you have 10 different bonds in the homework, fitting in there, right? So all the bond angle is fixed, so all these factors are going to complicate things. What if we put a dark cloth, like a magician's? We say, I don't worry detail about that. I just assume it's going to be a large bonds, and this bond is going to be representing a free joint chain. So you can use MB squared to describe your PET molecule, and they're beautiful, right? So B, physical meaning is just averaged bond length that will give you ability to describe the molecule by free joint chain. Okay? That's a statistical value of B's meaning. It's not a direct measurement how long that length is, because that length is not equal to free joint chain length. It's just a hypothetical length, B, that could describe or translate a real molecule to be a Gaussian coil. Okay? But typically, the longer the repeating unit, the n within a molecule, that will translate to a bigger B value. Okay? They're correlated, but not necessarily one-to-one. Any more questions? If not, then let's finish today's class. So let me say two things about next class. So next class, we're going to talk a little bit about one-like chain. So once we finish the one-like chain, we have one more thing to describe is how do we measure the end-to-end distance in experimental way. So we're going to cover radius of gyration in 2 lectures, and that is a useful parameter. Radius gyration is a parameter how we measure the molecular size. End-to-end distance are very hard to probe, so we measure the radius gyration. Once we finish everything, then that's pretty much finishes this particular chapter to talk about chain statistics. Okay, so let's wrap up today's lecture, then we come back again on Thursday.
You took a picture of the polymer and it was 1080 by 1080 pixels. You wanted to text it to somebody, but you could only text a 240 by 240 picture. How would you compress that polymer into smaller